Gauss's law, which we had talked about, relates this quantity called electric flux. So let's just define that again. Electric flux over an area, assuming it's a uniform electric field, and we'll talk about how to deal with that, non-uniform fields, in a second. This phi sub E is just the electric field. Dot product with a normal vector, a unit vector that's normal to the surface times the area of that surface. And so if you're looking at a closed surface, like a box, then Gauss's law is the sum of all that electric flux over the closed surface, telling you something about, or being equal to, the charge inside the box divided by the constant epsilon 0. So this is over a closed surface, this summation. And remember we talked about how n hat points towards the exterior. It's a unit vector, so it has magnitude 1, and it's perpendicular to the surface, and it's always pointing towards the exterior of the closed surface. So it's essentially giving us the positive direction of flux. Okay, well, flux is a scalar quantity, but it's giving us the positive sign of flux. Flux, if you have a field that's pointing out of the box, it's going to give you a positive flux. Field pointing into the box gives you a negative flux. Now, we've been dealing with boxes. What happens if you have just any closed surface? So here's just some generic closed surface. How do you deal with a situation like this? You have electric field, say, pointing in various directions on this surface, and it might even be in different magnitudes. Okay. Well, you can still sum it all up by breaking up the surface into small pieces of area, where each piece has a size delta A, and just thinking about dividing up this closed surface into just lots and lots of little squares of area delta A, and then finding the electric flux over each one of those pieces. And we're making the approximation that the electric field is mostly uniform over each of those little pieces, and of course, the more accurate that's going to be is when you're going to is having a flux over smaller and smaller pieces, divided up into smaller and smaller pieces, and just have more of them to get you a better flux calculation. And so if you do that, what does that become? That's an integral, right? That's an integral. If you're taking the limit essentially as these little pieces of area get smaller and smaller, then the more formal definition of Gauss's law looks like this, where the integral of the dot product of E dot n hat times the differential element of area dA, and taking the integral of that over, again, a closed surface, is equal to charge inside over this constant epsilon naught. Has anyone ever seen this notation before? Just an integral sign with a little circle through it? No? Okay. Well, you may run into it. It's just a symbol that means it's over a closed surface. Okay. We'll typically write over a closed surface here, but it means you're not really taking a limit from one point to another like you do in a typical closed definite integral. It's mostly you're starting at one point and wrapping around the whole surface and coming back to the starting point. So you're encompassing the whole thing. So that's what that little circle. Very end of class last time we had talked about calculating the flux over this. For this particular example, we had electric field 1,000 volts per meter on this surface, 800 everywhere else, 400 here. Well, let's just try it again. I mean, we should be able to figure this out. Let's just work through it. Remember, we had talked about, again, the direction of n hat, so be careful with the sign here, and just try it one more time. Let's go Let's go about 30 seconds on this. We should be able to try to come up with something in about 45 seconds. Answer number 2, which was 0.36 volts per meter, or volts times meter, excuse me, not volts per meter. This is a flux measurement, not a field measurement. And so we said that on this surface, the flux was what sign? Positive, right? So we get positive 1,000 volts per meter times, what was the area? 0.02 times 0.03. And that gave you, was it 0.6 volts times meters on this side? So this is the right side. And on the left side, be negative, and it was 800 times 0.02 times 0.03. What does that give you? Oh, sorry, 400. Sorry, 400. 400 times 0.02 times 0.03 gives you what? Negative 0.24. And then everywhere else, the flux was 0. Okay, so phi equals 0 here. Okay, and so you add those up, and so the total electric flux over the closed surface, so essentially the sum of all these E dot n hat d delta A's, gives you 0.6 minus 0.24, which was 0.36. So the next question then is, what's the net charge inside the box? Okay, so you now know the flux. Gauss's law should be able to give the charge. Remember that this constant epsilon 0 is 8.85 times 10 to the minus 12 in units of Coulomb squared over Newton meters squared. Okay, it's got to be 3.2 times 10 to the minus 12 coulombs. All you do is just do what? Multiply by epsilon naught, right? Because you're just bringing that epsilon naught to the other side of the equation. Multiplying this total flux over the closed surface by epsilon naught gives you, and we know the flux is positive, so the charge net flux is positive. So the net charge inside is positive, 3.2 times 10 to the minus 12 coulombs. Doesn't say anything about where the charge is. Doesn't even say that there can't be charge outside. This is kind of a contrived example where we have sort of 3 different uniform fields. But you might imagine something like, kind of like the example we showed the other day. Maybe there is one charge plate here, another charge plate here, and this box is sort of intersecting both of them and contains a total charge of 3.2 times 10 to the minus 12 inside. Again, the box, and what's more formally called a Gaussian surface, it's just an imaginary surface. It's not a conductor. It's not an insulator. It's not any material object at all. We're just using it as a sort of a conceptual idea rather than a real material object. Let's just do one more example here, and we'll require you to do all the flux calculations and find the charge itself. I have a funny-looking L-shaped figure here, and the dimensions, I'm not sure if everybody can read this, but the depth is 3 centimeters, the height is 3 centimeters, the height here is 6 centimeters, this is 3.5 centimeters, and then this is another length of 3 centimeters. So the total length here would be, from this end to this end, 6.5 centimeters. And you're given several different electric field values on the right side. This is E4, so we have E1 on the left side, E2 on the top, E3 on this intermediate top here, and then E4 on the right, E5 on the bottom. And E1 through E4 all have the same magnitude, 826 newtons per coulomb. E5 on the bottom, magnitude 600 newtons per coulomb. Go through, apply Gauss's law, see if you can calculate the magnitude and sign of the charge enclosed in this box. Okay, I'll give you a minute or so to work on this one. Really didn't talk about the front and the back, but you can assume, again, the front and the back have a field of 826 newtons per coulomb pointing in the same direction as E1, E2, E3, E4. So the only field that's different is on the bottom, let's say. Okay, big vote for answer number 3, which I believe is correct. A lot of people were getting that. We know it's got to be negative. Okay, and how can I tell it's negative? Just just by looking at it, how can I tell it's negative? Yeah, same area, but the fields on the top that are pointing in are larger than the field on the bottom pointing out, and so the top surfaces are going to give you what sign for flux? Negative. The bottom's going to be positive, but the top ones have a larger magnitude, right? So you can right away rule out any flux on what surfaces? What surfaces are going to give us zero flux? All right, the sides, right? Front and back, and the middle one, yeah, this kind of vertical L-shaped thing that's sticking up, that vertical surface on the L part. And so all we really have to worry about is the sort of the top two surfaces. So we have E2 times 0.03 times 0.03, and then E3 times 0.03 times 0.035, okay? And they're the same electric field, so it really is just that field times that horizontal surface area, okay? So we have E2 negative. And by the way, if you want to be just really formal about this, electric field E2 is pointing in the negative y direction, so I could write 0, negative 826, 0, dot product with n hat, but what is n hat on the top surface? What's n hat on the top surface? 0, 1, 0, right? It's in the positive y direction. So that's where our negative sign is coming from, right? And then we have 0.03 times 0.03, and then plus another negative 826, I'll just write in now, 0.03 times 0.035. What's the flux you get on those top two surfaces, the net negative flux on the top? Anybody work it out? Next, negative 1.6107 volts times meters. Does that look right? Any confirmation there? Okay, so this is the flux on the top surfaces. And then you have the flux on the bottom surface, which is 0, negative 600, 0, pointing in the downward direction. But what's the direction of n hat on the bottom? 0, negative 1, 0, right? So we're going to get a net or we're going to get a positive flux on the bottom. The signs will cancel. And then it's 0.065 times 0.03, right? Is that the correct area? And what do you get for the bottom flux? 1.17. So when you add those together, the total is negative something. Negative 0.44. And that's in units of volts times meters. So the charge inside is epsilon 0 times the total flux, or answer number, what were we saying? 3. Negative 3.9 times 10 to the minus 12. And the units, of course, are coulombs. Okay? Everybody okay? Questions here? Okay. So just examples of some calculations. Gauss's law has a number of different uses, and it's one of these concepts that physicists like a lot because you get to use it to do certain types of proofs in a sort of very elegant and intuitive way, or I should say a way that involves symmetry rather than just lots of brute force calculation. And you can use it to show some things that that were kind of difficult to show without it. One thing to think about is, where does this constant epsilon naught come from? We know that the flux had something to do with the charge. How do we know it's the correct constant? Well, one way you can prove that is, imagine you have just a point charge. Okay, so here's a single positive charge, charge Q. And I'm going to imagine it's at the center of an imaginary Gaussian surface, which is spherical. Okay, so this is a Gaussian sphere, sometimes it's called. So I have a charge in a closed surface. And I want to think about how to apply Gauss's law to this situation. And so we have E dot n hat dA is equal to the charge inside divided by epsilon naught. And this is one of a very small number of situations where you can actually use Gauss's law to calculate the electric field on the surface. So what it involves is doing some geometric reasoning, thinking about the symmetry of the situation and thinking about how to use that to make an integral that's kind of easy to do. So let's imagine we already know what the answer to this question is. We already know how to figure out the electric field due to a point charge. But let's, for a second, assume that we don't. All we know is that the charge is positive, and we know it makes an electric field. But you could do some reasoning about the symmetry of the situation. And you could say that, okay, I know that no matter what direction I'm looking at the charge, it looks the same, right? I can rotate the charge around in any direction I want. It looks the same to me because it's just a point. It has spherical symmetry, right? So everywhere over the surface of this sphere, the electric field has got to look the same. It's got to be pointing radially outward. So that's our electric field. And it has to have a uniform magnitude across over the surface of that sphere, because if it didn't, if some side had a smaller magnitude than another, then it wouldn't have spherical symmetry. It would look different from different angles, and that just doesn't make any sense based on the symmetry of the situation. So even without doing any calculations at all, purely from the symmetry, we could reason out that the electric field has got to be uniform over the spherical surface. It's either got to point radially inward or radially outward, and we know it's positive, so it's got to point outward. Okay. Well, once we do that, then we can think about calculating the flux over any part of this sphere. And let's again imagine breaking the sphere up into little pieces of area delta A or dA. And so there's an electric field, and here's the little piece of surface area. And n hat is pointing in what direction? To the right, okay? So there's n hat. And so what do you know about the electric field and n hat? Their directions are the same, okay? What if I looked at, say, a piece of area down at the very bottom? Same thing, right? The electric field is pointing down, and n hat's got to be perpendicular to the surface, and so it's got to be pointing in the same direction. So no matter which piece of the sphere I look at, n hat is always going to be parallel to the electric field. So the dot product, if I say the magnitude of E times the magnitude of n hat times the cosine of 0 degrees, dA, and cosine of 0 is 1, and the magnitude of n hat is 1. So that's just going to give me the electric field magnitude times dA. But what did we just say about the magnitude of the electric field over the entire surface? It's uniform. So if this is a constant, I can bring it out of the integral. And so this boils down to an integral over a closed sphere of dA. We're just summing up all the area elements. If you just sum up all the little pieces of area over a closed sphere, what are you going to get? Surface area of a sphere. What's the surface area of a sphere? Not 4/3 pi r cubed. That's the volume. What's the area? 4 pi r squared, where r here is the radius of the sphere, okay, and that's the distance from the charge to the sphere because the charge is at the center. So we get the electric field times 4 pi r squared equal to the charge inside over epsilon 0. Or if I solve for the electric field, what am I going to get? Q inside over r squared times what? Times 1 over 4 pi epsilon 0. Look familiar? Better. Better at this point. So we get back the electric field of a point charge, okay, which is essentially where the electric field of a point charge comes from in a more fundamental sense. Gauss's law is really telling us nothing different than that. It's just a more sophisticated or more elegant way of doing it. And so had this constant been something else, it wouldn't have given us back the electric field of a point charge. So we know the constant has to be epsilon 0. That's essentially where that proof comes from. Okay. So using Gauss's law in cases of very high symmetry can actually give you value of the electric field. And it actually works for point charges or spherical distributions. So for example, I could do the same thing with a sphere of charge.